Hello and welcome to the Math 171 teaching lesson on solving exponential and logarithmic equations, section 4.4 in the Math 171 pre-calculus algebra textbook. This section is going to show us how to use the skills that have been being developed in the first three sections of this chapter about logarithmic functions and exponential functions, using those skills to actually solve equations with logarithmic and exponential expressions contained in the equations. So let me get this text section up on the screen. Here we go. Solving exponential and logarithmic equations. And the text makes a pretty big deal about the names of these properties and all, and I'm not making such a big deal about the names of the properties. You'll see here they talk about one-to-one properties and inverse properties and such as that. But not to get so bogged down in terminology, I'd really like to use our time together here to just help you see the basic mechanics of how you do this. What's the procedure for solving these equations? And it's actually a mixture of algebra and your exponential and logarithmic skills. It's a mixture of both. Excuse me. So what we're going to find is that our general objective with either a logarithmic equation or an exponential equation is to, first of all, do all the algebra that we can do with the equation. First of all, do everything we can do to simplify the equation down, and generally try to isolate either the logarithmic expression or the exponential term to one side of the equation, everything else on the other side. And in certain very simple situations, we'll be able to immediately solve it if we have a log expression on both sides of the equation or an exponential equation on both sides of the equation equal to each other, and then we can just say that log of something equals log of something, so whatever you're taking the log of on both sides just equals each other. That's what they call the one-to-one property. That's very simple. We're going to look at those to start off with, or similarly if it was exponential, equal to each other. But the more typical and more complicated situation is where you do all the algebra you can, and you come down to just one exponential or logarithmic expression on one side of the equation, and then you reach a barrier. You reach a dead-end point after which algebra can no longer help you. You can't multiply or divide both sides or raise it to a power or add or subtract anything. You have to actually change the very nature of the equation. And the key in those problems, which we're going to spend more time on, those problems are the ones where you actually change then the exponential equation into its corresponding logarithmic equation, or take conversely a logarithmic equation and change it into its corresponding exponential form. And interestingly, doing either one of those procedures or the other almost always allows us then to solve the equation. So that's what this is all about. Let's look at some simple ones for starters here, as they have in example 1 here. When you simply have something as simple as 2 to the x power equals 32, and yes, solve for x. Well, without even using a calculator, you may recognize 32 as being a power of 2. If you multiply 2 times itself 5 times, that is 32. So the rewritten equation, as they suggest, is that 2 to the x equals 2 to the 5th. And here's the point. Since both sides of this equation have the same base for the exponent, 2 to the x and 2 to the 5, they both have the same base, then it's honestly as simple as just equating the exponents. So the same base to the x power equals the same base to the 5th power. So the two powers have to equal each other, and in this case they're x and 5, so we have our answer instantly. X equals 5. which of course if you plug it in, it's obviously true. 2 to the 5th equals 32 to check your answer. Again, this is very nice if you have something that simple, and you will have a few like this at least in your homework and such. But the next one, log base 4 of x minus log base 4 of 8 equals 0. Well, we got two log expressions, both the same base, and if you simply do an algebra step and add the same thing to both sides, in this case add log base 4 of 8 to the left side and the right side, the left side it remains at being only log base 4 of x, and the right side becomes log base 4 of 8. So those two equaling each other, once again we see that we have the same base. It's not the base of an exponent this time, it's the base for a log expression. Both bases on both logarithmic expressions are 4. So since the log base 4 of x equals the log base 4 of 8, it's both the same log base, so therefore what you're taking the log of, so to speak, the x and the 8 are equated with each other. So very simply you set the x equal to the 8 and you've got it. Again, this is an application of what the text calls the one-to-one property, but it's honestly as simple as that. And it doesn't matter that the base is 4. If it was log base 17 of x equals log base 17 of 8, well, then you still have x equals 8. Just the point is that both the bases are the same. The next one reinforces that using natural logs. Natural log of x minus natural log of 3 equals 0. Well, add natural log of 3 to both sides of the equation, ending up with natural log of x equals natural log of 3. You don't even have to, interestingly, you don't have to use your calculator and find out how much is a natural log of 3. You don't have to do that. You simply recognize, well, we're taking the natural log of something, and that equals the natural log of something else, so those two things have to equal each other. So then the x equals the 3, and we have our solution. X equals 3. Now, for instance, if this had been natural log of 2x minus natural log of 3, you just have one more algebra step. You would then have natural log of 2x instead of just x equals natural log of 3, and so the point is the same. The natural log of 2x equaling the natural log of 3 implies that then 2x would equal 3. So instead of x equals 3, we have 2x equals 3. We divide both sides by 2, and we get x equals 3 over 2. X equals 3 halves, or 1 1/2. Works the same way. It doesn't have to be just x by itself. It still works. All right, 1/3 to the x power equals 9. Well, 9 itself is 3 to the 2nd power, and 1/3 is 3 to the -1 power. So here's a case where both sides of the equation can be rewritten with base 3. The left side, 1/3 to the x, is the same as 3 to the -1 to the x. And if you recall your laws of exponents, something to a power itself raised to a power, you simply multiply the two powers together, multiply the two exponents together. So 3 to the -1 to the x is 3 to the -1 times x, and -1 times x is just -x. So 3 to the -x, as they've written here in the rewritten column, 3 to the -x then equals 9, which is 3 to the 2. So what's the point of all that? To make both sides of the equation having the same base. So since the base 3 to the -x equals the base 3 to the 2 power, then therefore -x equals 2, and then simply multiply by -1, x equals -2. All right, what about e to the x equals 7? Well, this is a case where we cannot just get the same base on both sides. That's not possible here. So this means we are going to have to, for the first time here, even though it's not a complex looking equation, it's an equation that cannot be solved just by algebra steps. So or using the one-to-one property. So what we have to do here, first time, we have to take this equation and change it into its corresponding logarithmic equation. And what I'm telling you is, I think the simplest way to do this, it's slightly different than what they're displaying here in the text. What they're doing is taking the natural log of both sides of the equation. They're saying take the natural log of e to the x, and that's got to equal the natural log of 7. And that's entirely true. With any equation, if the left side truly equals the right side, and they are positive quantities, then it would be true that the natural log of the left side will equal the natural log of the right side. That's totally true, but I suggest that's not necessary. You can skip this step. Just jump from the first column, jump over this second column, come to the third column here, which is, of course, labeled solution. The point is this. If e to the x equals 7, then here's what we know. That x is the exponent that you raise e to get 7. So therefore, the natural log of 7, which is, of course, just the power you have to raise x to get 7, is x. Let me say that again. If it is true that e to the x equals 7, then it is also true that the natural log of 7 equals x. That's what's called the corresponding logarithmic equation to the given exponential equation. Every exponential equation, if you have it down simply to an exponential expression equals a quantity, every exponential equation has a corresponding logarithmic equation that the exponential equation can be rewritten as, and no more exponents. You have a log equation, whether it's natural log or a log-based something or other. Similarly, every logarithmic equation, once you've done all the algebra you can do and get the log expression, or natural log or whatever, on one side of the equation equals some quantity, then that equation can be transformed into its corresponding exponential equation. In other words, just the opposite, just the inverse of what we were just talking about. So, just as every exponential equation has a corresponding logarithmic equation, every logarithmic equation also has a corresponding exponential equation. And interestingly, the way this works out is typically one form or other, either the logarithmic or the exponential form is solvable, and the other one is not. And so whichever one you're given, if it is not solvable, the technique is simply to transform that equation into the other form and then solve it. And honestly, that's what this lesson then is all about. That we've already covered what this lesson's about right there. That's it. So let's go through the details then. So on the next one, natural log of x equals -3. This is part F of example 1. There is no way that you can punch that in your calculator, hit natural log of x equals, you just can't solve that equation unless you have a higher, fancier calculator. And there are some that will, but a TI-83 or 84 is not going to solve that for you. Anyway, that means there's no algebra you can do. What you have to do is literally transform the equation itself into its other form, and it's given to us in a log form, natural log form, so that means we have to transform it into an exponential form. And again, they go through a step in this second column that I say you don't need to do. There's nothing wrong with doing it. You can do it, but I'm going to suggest you don't have to do it. Here's the point. What they're doing is saying, since natural log of x equals -3, natural log of x is equal to -3, then therefore e to the power of natural log of x is going to equal e to the power of -3, and that's true. If you have an equation both sides equal to each other, then you can take e to one side of the equation equals e to the other side of the equation as an exponential power. But that's not necessary. You can just jump from this first equation right here to column 3 over to x equals e to the negative 3. How can we do that? Well, by understanding what natural log of x means. Natural log of x here means e to this power on the other side of the equation, e to the negative 3 power, is going to equal x. That's what statement natural log of x equals negative 3, that's what it means. It's telling us that the exponent you have to raise e to get x is negative 3. So we just jump to that equation, raise e to the negative 3 power, call it x, and we have it. And yes, you can then use your calculator and plug in e to the power of negative 3 and find out exactly what that is. It's a small number between 0 and 1. But essentially, we've solved it now. And saying e to the negative 3 is okay, depending on WebAssign, depending on the context, that's okay. Or you may need a decimal to so many places. But the essential point in part F of example 1 is that we could not solve natural log of x equals negative 3. So what we have to do is convert the equation into its exponential corresponding form, that e to the negative 3 equals x. All right. Now similarly on G, log base 10 of x equals negative 1. Well, you cannot solve that. You can plug that in your calculator, log, and then hit x, but you can't solve this. So the only thing we can do is change it into an exponential form. So since it's log base 10, the base of our exponent is going to be 10. And what's the power? Well, this number over here that the log is equal to, that's always the power, because a logarithm is an exponent. So the log of x, base 10, is negative 1, telling us that what power do we have to raise 10 to get x? We raise it to the negative 1 power. So therefore, the corresponding exponential equation is simply jump over this step here and just say 10 to the negative 1 power equals x. 10 to the negative 1 is just 1 over 10. That's how much x is, 1/10, or 0.1, however you want to say it. And to say log base 3 of x equals 4 is just telling us that 3 to what power is x? 3 to the 4th power is x. So just write that out as an exponential equation. 3 to the 4th equals x. Now they didn't put that here, but I'm telling you this verbally. Log base 3 of x equals 4. The immediate corresponding exponential form of that statement is 3 to the 4th power equals x. So 3 to the 4th equals x, meaning 3 times itself 4 times is x. So 3 times 3 times 3 times 3 equals x. And yes, 81 equals x. So we end up with the solution statement, x equals 81. So as they share in this box here, do whatever algebra you need to do in part 1 to rewrite the original equation in a form that will allow the use of a one-to-one property if it's a really simple equation that you don't have to transform it into its corresponding form. Those are nice, like the first 3 or 4 we did. Or if it's not simply solvable that easily, then you do all the algebra you can to isolate the exponential expression or the logarithmic expression by itself to one side of the equation equals to some quantity on the other side. And then they say apply the inverse property. Well, what I'm saying is just simply transform the equation, rewrite the equation into its corresponding form of the other type. So if it's exponential, transform it into a logarithmic form. If it's logarithmic, transform it into an exponential. So let's do some more examples. e to the x equals 72 here in example 2. Once again, you can't solve that straight out, so you convert it into its corresponding logarithmic form. We have base e, so we go to natural log. And again, I say skip this second step here, just go to this step. The natural log of, since e to the x equals 72, the natural log of 72 equals x. And then you can, yes, use your calculator now. What is the natural log of 72? To 2 decimal places is about 4.28. So, answer that one. The next one, you have to do a little bit of algebra first. 3 times 2 to the x equals 42. Just one minimal little algebra step here. Divide both sides by 3. And that, what does that accomplish? That gets the exponential expression 2 to the x isolated by itself on one side of the equation when you divide both sides by 3. So 3 to the 2x divided by 3 is just 2 to the x. 42 divided by 3 is 14. And 2 to the x equals 14, that's a dead end. You cannot solve that like it is. So instead, you simply transform this equation into its corresponding log form. And it's base 2 on the exponent, so it's log base 2. And we simply say the log base 2 of 14 equals x. So I suggest skip this line here and just jump down to log base 2 of 14 equals x. Now, how do you get log base 2 of 14? Well, yeah, you got to do a little work on this. You can't just punch that into most calculators, at least. Not the TI-83s or 84s unless they have a nice little change of base app in them. Some of the more modern ones do. So if you don't have the change of base app, for instance, mine doesn't have it, then what you have to do is use the change of base formula and either go to natural log of 14 over natural log of 2, or what I usually do is log base 10 of 14 over log base 10 of 2, and that's equal to log base 2 of 14 by the change of base formula. And then when you find those two numbers and divide the top one by the bottom one, you get roughly 2 decimal places, 3.81. And by the way, you can plug that back in. If you plug in 3.81 back into the original equation for x, 2 to the 3.81 power, multiply that times 3. Most of you know it's not going to come out exactly equal to 42 to check your answer, but that's not a problem. Because we rounded off this irrational number that the decimals go out forever, we rounded it to merely 2 decimal places, it's not going to check perfectly if we substitute it back in. It's going to be close. So instead of getting 42, we might get 41.9 something or 42.0 something, but that's okay. All right, here's one where once again we just have a couple little algebra steps to do and then proceed with our regular method. So example 3, 4 times e to the 2x minus 3 equals 2. Well, don't let the exponential expression embedded in the equation throw you here. Do the algebra that you can do to isolate the exponential expression first. All right, so let's go ahead and add 3 to both sides first. And when you do that, you end up on the left side with only 4 times e to the 2x. And 2 plus 3 on the right becomes 5. So 4 times e to the 2x equals 5, still continuing in process to isolate the e to the 2x. It's being multiplied by 4, so we're going to do the opposite of that and divide both sides of the equation by 4 to get the e to the 2x by itself. And then on the right side, 5 divided by 4 is just 5/4, 1.25, however you want to say it. And then, again, I suggest skipping this step of taking the natural log of each side. I'm not saying you can't do it, but I'd say you don't have to. Jump right down to the next step by using your understanding of what e to the 2x means and what natural log means. We have the base e. The exponent is 2x, and e to that power is 5/4. So that means the natural log, base E, natural log of 5/4 equals 2x. And so the natural log of 5/4 equaling 2x, now x is simply just divide both sides by 2 and you got your answer. A single x is just 1/2 the natural log of 5/4. And so you might be thinking about your log properties. It is true that x is also equal to the natural log of 5/4 to the 1/2 power. In other words, the square root of 5/4, and that is true. You're going to get the same answer. But you can leave the 1/2 just out here as a coefficient. So then all you have to do is find out what's the natural log of 5/4. Take 1/2 of that, round it to the required number of decimal places, in this case 2. X turns out to be approximately 0.11. And again, you could take that and plug it back in the original equation for x, and you would come out the left side being very, very closely almost equal to 2. Example 4 is really not any different. It's just got the exponent with a few more terms in it. So a little more algebra to do after we convert the exponential into its corresponding logarithmic form. So first of all, still, again, we do all the algebra we can do with what we're given. So 2 times 3 to the 2t minus 5 minus 4 equals 11. Well, that minus 4 is easy to deal with. Just add 4 to both sides, get rid of that. So the right side becomes 15. And then 2 times 3 to the 2t minus 5, our exponential expression, 3 to the 2t minus 5, is being multiplied by 2. So let's divide that side, both sides, by 2 to cancel that out, get the exponential expression by itself. So we end up with 3 to the 2t minus 5 equals 15/2. And that's a dead end right there. You cannot solve that one using algebra. We've gone as far as we can with algebra. So we convert. Since it's given to us in an exponential form, we convert it to logarithmic form. And so the base is 3, so it's going to be log base 3. The exponent is 2t minus 5, so that's going to be what the log equals. So log base 3 of 15/2 equals 2t minus 5. That's the exponent. So log base 3 of 15/2 equals 2t minus 5. And again, they've written it backwards. I would write it the other way around, but that doesn't really matter. So log base 3 of 15/2 is equal to 2t minus 5. So what can we do with that? Well, what we're trying to find is how much t is. So to get t by itself, we can do some algebra once again. We can add 5 to both sides. And then once you add 5 to both sides, to get the t by itself, it's 2t. So now just divide both sides completely all the way through by 2. And we do find out that t is equal to 5 divided by 2 plus 1/2 of log base 3 of 7.5. And yes, if you had to just come up with a single decimal answer to so many places, you would have to use the change of base formula and process that out to log base 3 of 7.5. I would probably go to log base 10. When I use change of base, I usually use log base 10. So log base 10 of 7.5 divided by log base 10 of 3 would exactly be equal to log base 3 of 7.5. And then take half of that and add 5/2. And when you do to 2 decimal places, it becomes about 3.42. Okay, so now let's do one that's very, very different. This is an exception to the procedure we've been discussing. Given an equation that is said to be in quadratic form. So what do we mean by quadratic form? It means that at first it doesn't look like your standard quadratic with an x squared in it, but it does have something squared. It just doesn't appear to be that way, so we're going to take advantage of it actually being in a squared format and factor the thing and solve it. So here's an exponential equation with two exponential terms in it, and the key here is that one of the exponents is exactly twice as much as the other one. That's what's necessary to use this quadratic form method to solve it, is that one of the exponents has to be exactly twice as much as the other one. And the third term can have no exponent on it at all. So here we go. Equation given. E to the 2x power minus 3 times e to just the x power plus 2 equals 0. And of course we're supposed to solve for x. Here's what the key to this problem is. The fact that e to the 2x, based on the rules of exponents, if you just take e to the x and square it, so you have e to the x squared, e to the x itself to the second power. Then you have e to the x and that to the power of 2. So we have something to a power, again to a power. And as we did a while ago with another problem, in that case we can simply multiply the two exponents together. So e to the x squared is actually e to the x times 2, and just change the order of the multiplication. It's e to the 2 times x, which is what we're given. But what we're going to do is then use that fact to change the e to the 2x into its alternate form, e to the x parentheses squared. So what does that mean? That means we have e to the x squared minus 3 times e to the x just to the first power plus 2. And so if you think of that e to the x as being like a variable, pretend and say y equals e to the x. Then we have y squared minus 3y plus 2 equals 0, and we've got a good old-fashioned quadratic equation in the variable y. Y squared minus 3y plus 2 equals 0. You could factor that into y minus 2 times y minus 1 equals 0. And then you get that y is 2 or y is 1. And there's nothing wrong with actually creating a variable like that and substituting for e to the x in these kind of problems. Some students prefer to actually do that. Solve it, say, using a y, and then come back after you find out y is 2 and y is 1, then come back and remember, oh yeah, well y equals e to the x, so e to the x equals 2 and e to the x equals 1, and then solve for x, and that's perfectly fine. They don't introduce a new variable here, they just simply work it out in this form, so I'm going to follow this through. Factoring this is nice because it works rather simply. When we factor this, it becomes e to the x minus 2 times parentheses e to the x minus 1 equals 0. This is just as if e to the x was a good old-fashioned variable like y or z or whatever. So now we're going to take each of these equations, each of these parentheses, and equate them to 0, because we know this times this equals 0, so either one or both of the parentheses is equal to 0. So setting each parentheses one at a time to 0, e to the x minus 2 equals 0, add 2 to both sides, we get e to the x equals 2. Or the other one, e to the x minus 1 equals 0, add 1 to both sides, we get e to the x equals 1. Well, getting these two equations then, e to the x equals 2 and e to the x equals 1, then leaves us two rather simple little equations that we have to solve by the methods of this section. One-to-one property doesn't work, so we have to transform these two exponential equations into their corresponding log form equations. So e to the x equaling 2 means that the natural log of 2 equals x. Well, that's an answer, natural log of 2. E to the x equals 1, that means the natural log of 1 equals x. And so if the natural log of 1 equals x, that means e to the x power equals 1. E to the what power is 1? 0. So x equals 0. So we have two solutions, 0 and natural log of 2. Now, you say, can you leave it like that? That just depends on what WebAssign says, or what does the test say, whatever. How do they ask you to do it? For instance, if you try to type in natural log of 2 and it marks it wrong, then they probably want a decimal, if they don't tell you. But anyway, natural log of 2 to 2 decimal places is approximately 0.69. So the two answers are x equals 0 and x equals 0.69. That's the two answers we get. Now, because we had a quadratic equation, we've got to check our answers and see if they work. And the truth is, if you plug in 0 for x or 0.69 for x, both of those will work. It will work. So both of those are good answers. But let's look at a problem where it can get a little more involved and it's not quite so simple. For instance, sometimes we come up with what are known as extraneous solutions. And let's jump down to this one right here. On the screen in front of us, it says solve natural log of x minus 2 plus natural log of 2x minus 3 equals 2 times natural log of x. Now, this equation looks a lot more complicated than what we've been seeing, and in one sense it is. It has 3 natural log expressions in it. But what we're going to do is make an objective of trying to get just one natural log expression on each side of the equation, set them equal to each other, and then use the so-called one-to-one property. And since natural log of something is going to equal natural log of something, the two somethings, so to speak, are equal to each other, and we'll get our answer for x. So actually, this is one we're not going to convert into exponentials, but we're going to have an issue with extraneous solutions. So let's go through this. Natural log of x minus 2 plus natural log of 2x minus 3 equals 2 times natural log of x. Well, first off, on the left side of the equation, I want you to notice natural log of something plus natural log of something is very much like what we had in the previous section, properties of logarithms, that the logarithm of something times something is equal to the logarithm of the first something plus the logarithm of the second item. And so actually what we have here is a case where we can use that product property of logarithms backwards. So we can say, since we have the natural log of something plus the natural log of something, actually that's going to equal just one time, the natural log one time of the x minus 2 times the 2x minus 3. And that is what they do right here in this line that I'm wrapping around right here with the cursor. The natural log of the product of those two, x minus 2 times 2x minus 3, then is equal to 2 times the natural log of x. But what else have they done on the right side? That they've gone ahead and silently done a step. Once again, using the properties of logarithms. If you recall this second property, if you have a coefficient in front of a log expression, you can remove the coefficient from the front and put it as an exponent on whatever it is you're taking the natural log of, or log base, any base of. So this 2 out here can become an exponent on the x. And they do that so that the right side becomes natural log of something, just natural log of x squared. The left side is natural log of these two multiplied together. And we got to multiply that out and FOIL that out, so to speak, so that we know what we're taking the natural log of, and it turns out to be natural log of 2x squared minus 7x plus 6 is equal to natural log of x squared. So we had to do this step with the 2 up here because in order to use the one-to-one property, you cannot have a coefficient in front of natural log on one side and not on the other side. Both sides have to have the same coefficient, reduce it down to a coefficient of 1 for both of them. So that 2 has to be appended up here as an exponent onto the x. So now we have the natural log of something equals the natural log of something, and so therefore the 2x squared minus 7x plus 6 on the left side equals the x squared on the right side. Finally, we're out of the natural logs, just back in the good old-fashioned quadratic algebra now. All right, so we have a quadratic equation in x. Let's subtract the x squared from both sides to get all the terms on one side. And then we have 2x squared minus x squared is just x squared, and then minus 7x plus 6, all that's equal to 0. And wouldn't you guess, a nice simple one. You can just factor this real easy into x minus 6 times x minus 1. So the two answers are x equals 6 and x equals 1. And you think, oh, I got this all done, now I can jump up and get back to my TV program. Well, maybe not. Maybe not, because we had to put these two natural log expressions together, and we created this quadratic in x, and sometimes creating quadratics like we used to do with those radical equations can introduce extraneous solutions. So let's see what happens here. Class, we are obligated to check both those answers, the 6 and the 1. They both may be valid answers. They both may be no good, bogus, extraneous solutions, or one might be valid and one might not be valid. Let's find out. When you check both of these, let's do the 1 first. And actually, we're going to find this out really quick. When we plug in 1 for x and see what happens, we get natural log of 1 minus 2. Problem. So we're attempting to take the natural log of negative 1. I trust most of you will recall it's not difficult, it's impossible to take the log, natural log, any kind of log of a negative number. Because there's no power that you can raise e to get a negative number that's a real number power. Yeah, complex number power is okay, but not real number powers. So the natural log of negative 1 is a meaningless expression with real numbers. So immediately we see it doesn't work. And right here, 2 times 1 is 2, take away 3 is negative 1. Again, we're trying to take the natural log of negative 1, but the point is, even if you just have to do it one time, it's bogus. So 1 apparently looked like a solution, but it's not. It's what we call an extraneous solution. But when we plug in 6, a neat thing happens. Natural log of 6 minus 2 is 4. Plus natural log of 2 times 6, 12, take away 3 is 9. Is that equal to 2 times the natural log of 6? Well, let's think about it. Natural log of 4 plus natural log of 9. We can use this same product property with natural logs. Say the natural log of 4 plus the natural log of 9 is natural log of 4 times 9, which is natural log of 36 on the left side. And over here we have 2 times the natural log of 6. But once again, using this property of logs, the power property, we can put the 2 as an exponent on x, which is 6. So we're saying natural log of 6 squared, and 6 squared is 36. So yes, both sides turn out to be natural log of 36 equals natural log of 36. Perfectly fine. 6 is a valid solution, and it's the only valid solution. What that then takes us back to, we sort of jumped over this, is just let me go through an example or two of solving logarithmic equations by the technique of changing the logarithmic equation into its corresponding exponential form. So again, that's not how they tell you to do it. They say take the logarithmic form, and they call it, here's the term, it's a perfectly good term, they say exponentiate each side. In other words, take each side of the equation and turn it into an exponent on e. In this case, it's natural log, so the base would be e. And that's perfectly true, it's fine, but then Then you have to go through another step and realize, oh, e to the natural log of x, yeah, that's right, that's x. But I say just change the equation form, one step. Natural log x equals 3 is the same as e to the 3 equals x. So x is e to the third, period. Done. Now, however you wish to do it, it does not at all matter to me. I'm just trying to show you what I say is the easiest way. Now, if you have, for instance, natural log of 3x equals 2, the corresponding exponential form is e to the 2 is equal to 3x. In other words, e squared equals 3x. Well, then x is just e squared over 3, or 1/3 of e squared. If that's fine, that's the precise exact answer, then you got it. Or if they want a decimal, use your calculator, find out how much e squared is, take 1/3 of that, it comes out to about 2.46. Here's another one that works out nicely with the what they call the one-to-one property. You don't have to change it to an exponential equation. If you have log base 3 of 5x minus 1 equals log base 3 of x plus 7. The key here is both the log bases are the same. Happens to be 3, but they're both the same. So since log base 3 of something equals log base 3 of something, those two somethings, as I like to say, are the same. So 5x minus 1 does equal x plus 7, and you do a couple little algebra steps, subtract x from both sides, add 1 to both sides, and you get, first you get 4x equals 8, and divide by 4, and you get x equals 2. And when you check back with 2 into the equation, it works. 5 times 2 is 10 minus 1, log base 3 of 9. And log base 3 of 2 plus 7 is 9. So log base 3 of 9 equals log base 3 of 9. It checks. And if you have one like this here, 2 times log base 5 of 3x equals 4. Well, let's do one algebra step to get the log expression isolated by itself on the left side. Right now it's being multiplied by 2, so let's get rid of the coefficient of 2 by dividing both sides by 2. So log base 5 of 3x is 4 divided by 2, which is just 2. And that means we're stuck now. Can't solve that equation like it is. I'm going to skip over this step they did and jump down to this next step, which tells us that interpreting log base 5 of 3x equals 2 means that the base 5 to the 2 power is equal to 3x. So I just come down here, actually between just above the 3x equals 25, I would write it right in there, just the fact that 5 squared equals x. 5 to the second power equals, 3x. 5 squared equals 3x, and 5 squared, you can do that, that's 25. So since 25 equals 3x, you're just trying to find out how much 1x is, divide both sides by 3, x equals 25/3, and you can plug that in and check it, and it works. So sometimes you have to do a little bit of algebra first, then take the logarithmic equation or the exponential, whichever it is, and change it into its corresponding other type, and then solve. And even then, sometimes you have to still do some more algebra, but as has been said before, it's just algebra. And one other thing I want to show you in this lesson, this is sort of a practical kind of thing. If you're putting some money in the bank at a certain interest rate, and you might just happen to wonder, well, how long is it going to take for that money to double? It's a reasonable question. So here's a problem. You've deposited $500 into an account that pays 6.75% interest, and it's compounded continuously. How long will it take your money to double? Well, let's figure out how to solve this. Notice it says compounded continuously. That means of the two compound interest formulas of that previous section, we're going to use the one that has E in it. The formula for continuous compounding is simply A, the future account balance, is equal to P, your starting principal amount, times E to the RT, where little r is the interest rate, not as a percent, but as a pure decimal, converted the percent into a pure decimal. So A equals P times E to the RT is your base formula for continuous compounding. Now, what do we know? Capital P, the principal amount, the money we started with, is 500. Little r is 6.75%, which as a pure decimal, moving the decimal point 2 places to the left, is 0.0675. So 0.0675 becomes, now listen to this, it becomes the coefficient of t in the exponent on E. 0.0675 is the coefficient of the variable t inside the exponent that's on E. So the exponent on E is 0.0675 times t. Well, now they don't tell you this, and I'm going to tell you that actually I fault them, they should tell you. They just say 6.75% interest. And they don't tell you how often it's earning that, but I trust most people understand that means once per year you earn 6.75%, but they should tell you that. It's not per month or per day or anything else. It is 6.75% per year. So that means T then is in years. And now to find out how long it's going to take to double, here's where we do a clever little trick. We already know how much money it's going to turn into. We just don't know how much time it's going to take, because we know how much money it's going to turn into. We start with 500 and it's going to double. So 500 becomes 500 times 2 becomes $1,000. So that means we know 3 of the 4 unknowns in this equation. A equals P times E to the RT. We have A, P, R, and T that we need to know, and we know now 3 of the 4, so we can, yes, use an equation and find the 4th one, T. So what we do is let A equal 500 times 2, which in this case is 1,000. So 1,000 equals the principal P 500 times E to the 0.0675 T. And they have it written here just exactly the opposite of how I just said it. They have the 1,000 on the right and the rest of it on the left. But anyway, however you write it, it works either way. And then back to the methods of this section. We want to isolate the exponential expression. E to the 0.0675 T is being multiplied by 500, so we're going to divide both sides of the equation by 500 to get the E expression by itself. So E to this power is now equal to 1,000 divided by 500, comes down to 2. So now we have an exponential equation that we cannot solve by algebra, so we must convert the exponential equation into a logarithmic equation. It's base E, so therefore it's natural log. And so E to this power equals 2 means that the natural log of 2 equals 0.0675 T. And once again, they've written this exactly opposite of how I just said it. They have the 0.0675 T equals natural log of 2. Same thing, just opposite sides of the equation. It's fine. And now all we care about is how much T is. So T is being multiplied by 0.0675, so we divide both sides by 0.0675. And quite properly, we say that T equals the natural log of 2 divided by 0.0675. But if you have to just come out with a pure decimal answer, then you have to use your calculator and get how much natural log of 2 is, and you get that number, and then divide that natural log of 2 number by 0.0675, and you get a little bit more than 10.27 years. So it's a little more than 10 years and a fourth of another year, a little bit more than that. So a little point to be made right here too. This easy mistake to make. This natural log of 2 divided by 0.0675 is not the same as natural log of 2 divided by 0.0675. So it's not the natural log of these two numbers divided one into the other. No, it's the natural log of 2 all by itself. Get that number, whatever it is, and then divide that number by 0.0675. Okay, just a point of caution there at the end. So I once again hope this has been helpful for everybody. This is the next to last section we're going to do in this chapter. There's one more section that we're going to do, the 4.5 section in this chapter, and then we're also going to do some sections in chapter 8 before the final exam, but there's only one more section in this chapter. So I'm going to close this out here. Like I say, I really do hope this is helpful to clarify lots of points and techniques and these methods of solving these exponential equations and logarithmic equations. So I wish everybody well in your work on this, and have a good rest of the day here.